A very good morning to one and all present here. Good morning, Dr. Jitendra Tembur sir.
Good morning.
I welcome you for our today's day 4 session, which is based on high performance computing using parallel distributed and cloud computing. Today we have Dr. Jitendra V. Tembur sir from Indian Institute of Information Technology, Nagpur. Am I clearly audible to everyone? Okay. I welcome you, Dr. Jitendra Tembur sir from IIIT Nagpur. Sir is from Department of Computer Science and Engineering. Sir has completed his PhD from VNIT Nagpur. Sir is currently working as a head of department and assistant professor at Indian Institute of Information Technology Nagpur. Sir is having around 15 years of experience. He has started his career from the year 2005. Sir has received many funding research grants under SERB, Atal FDP. Sir having the certification in IBM DB2 by IBM India. Sir worked as a visiting faculty at many places. Sir having many publications covering Scopus, Sky, Web of Science journals. Sir also worked as a member in technical review committee at various places, including International Conference on Cybersecurity, International Conference on Data Engineering and Communication Technology, Warangal. Sir also worked as a reviewer for international conferences at various places. Also, sir reviewed many journal papers, book chapters, including the Springer series. The main area of expertise of Dr. Jitendra Tembur sir are big data and data analytics, information security, database management systems, algorithms, parallel computing, theory of computations, computer architecture and organization, data mining, and warehousing. Sir, I welcome you on behalf of Information Technology Department, and I request you to start with the session.
Okay, thanks for your introduction. So we're going to start today's session. I'm going to share my PPTs. So am I audible clearly?
Yes, sir. Sir, some echo is there. You are audible, but some echo is there.
Okay. So let me change my position. So am I audible clear now?
Yes, sir, audible.
Yeah, fine, thanks.
Sir, we are having two sessions with you today. One will
Yeah,
be
yeah.
till 11:30. Then, with some break, we will start our session at 12 p.m., which will be 1:30.
So is my PPT visible?
Yes, sir, it is visible.
Now it's moving.
Yes,
Slides are getting changed.
yes,
Yeah,
yes, sir,
okay.
yes, sir.
Yeah, fine. So welcome to all those joined for this particular session. So today we are going to see OpenMP. So in the first 1 hour, we are going to see what are the concepts that are there in OpenMP, which is called as Open Multiprocessing. And in later half, that is a 30 minutes, we are going to see hands-on on that, so that how we can use OpenMP to parallelize the program. Fine. So we'll start the today's now of this particular talk. So I'll brief out what exactly is multiprocessing, which is already known to you. So, and what is a parallel processing and motivation behind the parallel processing. So multiprocessing means the multiple processors using two or more central processing unit, okay, with a single computer. We are having a single computer, and on that we are having two or more central processing unit. So nowadays it is a de facto. All the desktops, all the laptops, nowadays they are having minimum 2 cores and more than that as per the configuration. So that means we are having the infrastructure to perform parallel computing. Okay, in olden days it was not like this when we are having only one processor. But with your mobile, with your laptops, with your desktop, all the parallel computing hardware is available with you. Just what you have to do, you have to exploit it. Okay, so for that exploitation, we have to write we have to use particular programming language. Okay, so in this case, we are going to see OpenMP, and in the later half, we are going to see NPI. And what is a parallel processor? Just the simulation use more than one CPU or processor to execute a program or multiple computation threads. That's all. It is not very big that parallel processing. Just what we are doing, we are processing or we are executing a particular task on a number of processors or the number of cores that are available on hardware. Okay, I am saying a hardware, fine. Because in parallel processing we require exclusive hardware where we are having infrastructure, fine. And the motivation are this. So first motivation is high speed, solving problem faster, high throughput. So high speed means what? We are having a infrastructure where we are having a number of cores, yeah. And we want to solve the problem somewhat faster. Take an example of weather forecasting. Then you can take an example of stock exchange. You can take the example of like some scientific computation, okay, where we require to solve the problem fast. Then next is a high throughput. So high throughput means we will going to give the large amount of task to a particular processor, and it will be able to execute that. That means throughput exactly the number of instructions that we are executing, okay, or solving more instances of given problem. That means we are having a large amount of data even, okay, and then that large amount of data need to be processed with the help of the particular algorithm, and then we want to process. So if you have only one CPU, so it is very difficult, means it will going to execute, but it will going to consume lots of time. But if you are having a large number of processors, so in that you can divide the entire data, and that data will get executed by the program which you are parallelizing. Then the next one is higher computational power. So that we are having nowadays. Higher computational problem means we are having a many core CPUs, we are having a multi-core, many core GPUs. So this infrastructure is there, and that is generally used to solve the large problems. So here, whenever you are targeting or whenever you are exploring parallel computing, you have to see what are those particular challenges in terms of solving the problem, in terms of having a large computation, in terms of having a large data, and then that you can target towards parallelize, okay, so that you can speed up, okay, you can achieve high throughput, and you can able to solve larger problems. So this is the brief introduction which we supposed to have. Then moving towards what is a OpenMP. So OpenMP is an application program interface. That's all, nothing else. Okay. So and by default, OpenMP is available whenever you are installing any Linux operating system. Okay. In Windows operating system, you have to install separately but in Linux it is by default available. So just whenever you are installing a GCC compiler, so that time OpenMP is available with that. So it is simply an application program interface that may be used to explicitly direct multi-threaded shared memory parallelization. So it is used for multi-threaded, that means you can create multiple threads and that too on shared memory parallelism. That means it is applicable on a machine or a desktop or a laptop there only, okay, where you are having a shared memory which will be accessed by a number of threads. And when we are using OpenMP, what we do, we target towards to see whether there is any loop. So we are parallelizing the loops because we know that in the loop we are having large amount of computation if the iterations of that loops are very large, okay, in thousands or in lakhs. It is possible we can have that bigger loops as well, fine. So in OpenMP we target the loops and that loops we are parallelizing. And moreover, it offers an incremental approach to parallelize. That means you need not to rewrite the complete program either in C or C++. So here we will be able to see the interface with respect to C and C++. Right? So you need not to rewrite a sequential program which is written in C and that you have to convert in OpenMP. No. You can use that program as it is. Only certain things that are required for OpenMP, that just you have to add it. That's why it is called as incremental approach. Okay, so incremental approach in such a way that just some particular line of code we have to add in a C program, so your program will going to become OpenMP program. Fine. So this is OpenMP. Now what OpenMP provides to us, what are the facilities? So OpenMP is generally meant for the user to do these 4 tasks. So first one is create team of threads for parallel execution. So it will help you to create as many threads you require to solve the problem in parallel. Okay. Second, specify how to share work among the member of team. So you are creating a number of threads, okay, and those threads need to perform some task. Yes. So you have to specify that what are the particular tasks that has to be done by particular thread. Okay, so most of the time in OpenMP this has been done internally automatically. Only we have to think what will be that particular data which need to be get executed by a particular thread. Only that we have to take care. Other things OpenMP automatically take care. Next, it helps you to declare both shared and private variables. So this is one of the important concepts in OpenMP, that in a program we use so many variables. Yeah. So those variables need to be shared or they need to be private. So that we have to specify exclusively, because with the help of shared variables and private variables, it is very easy for us to control the particular variables and then we can easily parallelize. Fine. So we will see that in detail when we are going to see the program. Next is synchronize threads and enable them to perform certain operation exclusively. That means here we have to create so many threads that threads will be able to share the work, okay, and that work and whatever they will be able to share, that can be shared, that can be private or that can be public or that can be shared. So in this case we require a kind of a synchronization. Synchronization is required. Why? Because it is possible that certain thread can execute the work fastly, okay, and certain thread can execute the work little bit slowly. So whenever a team of thread is created, so all the threads need to execute the task and then they have to go further to visit another code where they are taking part. Fine. So that is the synchronization of threads is very important, and that facility is also provided. Now moving further, what OpenMP is not supposed to provide. Okay. So these are the different 5 points OpenMP is not providing. So OpenMP is not meant for a distributed memory system. Okay, so for distributed memory system you cannot apply OpenMP, but if you are working in distributed memory system or parallel system, so you have to take the help of message passing interface. Next, OpenMP is not necessarily implemented identical by all vendors. So nowadays there are so many vendors, okay, they provides OpenMP. So OpenMP organization is a one vendor. Then there is a GCC. Then there is a Intel, okay. Then there is a PGG group is there. So these are the different vendors. Even IBM is having its own what we can say OpenMPI software. Fine. So it is not say necessary that all the vendors are providing similar kind of implementation. Fine. Then OpenMP is not guaranteed to make the most efficient use of shared memory. Okay, so though this is made for shared memory architecture, but it is not giving you any guarantee. Fine. Next, required to check, OpenMP is not required to check the data dependency. So data dependency, data conflicts, race condition or deadlock, this will be not done by OpenMP implicitly. Okay, these are the things which we have to do directly by us as a user. Have to identify what is the data dependency, what is the data conflict, what is the race condition and deadlock, and then that need to be get rectified, and then the program can rewritten to read out of these particular problems. Then next, OpenMP is not designed to guarantee that the input or output is the same file is synchronous when executed in parallel. The programmer is responsible for that. Okay, so whatever the input file which you are giving to the program and whatever the output is produced by your program, fine. So OpenMP is not taking any responsibility of synchronization of that. Programmer need to do that particular thing and need to synchronize the input and output. So these are the different things that OpenMP does not support, okay, exclusively. So moving further to see the more functionality of OpenMP. So what is the OpenMP programming model? So with this particular figure you can easily understand the OpenMP programming model. What it is the set of, or it is a pair of fork and join. Okay, so in your program we will have always one thread, okay, which is called as a master thread, or you can say the initial thread, something like that. So this is the thread. What it does, it forks the team of threads, and then this team or threads will execute the task in parallel. Once the task is finished, these all threads will join, and then the control will be given to the initial thread or the master thread. So this is the fork and join phenomena is adopted in OpenMP. So wherever we are seeing this single thread, that means this is the serial reason. Wherever you will going to see multiple threads, this is the reason where we are expecting to perform the task in parallel. Okay, so here the task will be done parallel by all the threads, including the threads who initiated the team of threads. Okay, and then once the job is over, the control is given to the master thread or this thread who initiated the task, and then once again there is a serial reason. Then likewise you can have another parallel reason where there will be a fork and join. Fine. So this is a very simple model which is just using fork and join, and this we need not to do. This everything will be done by OpenMP internally. Just we have to specify the parallel reason. The moment you will specify the parallel reason, okay, the team of threads will be created by the OpenMP. Fine. Moving towards further, OpenMP programming model is based on all these 5 parameters. So first one is, it is a shared memory, thread-based parallelism. So on shared memory, you will have threads, and those threads will going to achieve the parallelism. Next, explicit parallelism. It is not an implicit parallelism. Fine. Explicit means programmer will write the program, in that it will specify the number of threads, and then those threads will going to execute the task. Then the third point, fork join model. So it is using a fork join model. The fork will going to create the threads, and join will going to combine all the threads, and control will be given to the initiator thread or a master thread. Then next, it is a compiler directive based. Okay, so it is not very new. Only the compiler directives are available. Just those compiler directives we have to add in the program. Okay, and our program will going to become OpenMP program. And the last, it is nested parallelism supported. That means nested means the parallel reason within parallel reason. This kind of support is provided by OpenMP. So these are the main theme, or these are the main features. Based on that, we can able to utilize OpenMP programming model. Fine. So moving further, so we are going to see the first C code which is written in OpenMP. Okay, just a skeleton we want to see, and that we want to map with the fork and join concept. Fine. So now in the program you have to add openmp.h. Then your main program will start. In the program you will have many variables. Some serial code will be there. Okay. And then somewhere there will be a beginning of parallel section. So parallel reason will start at this particular point. What will happen here? Fork a team of threads. So team of threads are get created. So that can be specified using hash pragma omp parallel private variable 1, variable 2, whatever may be the variables they are private, whatever may be the variables they are shared, we have to specify. So this is the point. Okay, this is the point for the compiler. What it will do? It will fork the team of threads. So when the team of threads are created, the whatever the code which will be written in this curly bracket and this curly bracket, that means this is the code. This code will get executed by all the threads including master. Okay, all the threads including master. And here the parallel reason ends. So all the thread will join and control will be given to the master thread. So this is the way we can just at a particular place we have to add this kind of statements, and your program will going to become OpenMP program, and this header file we have to add. So that's why it is called as incremental programming. Just whatever it is required that you have to add inside the code, that's all. And then after that there will be another serial code, and after that you may have some another parallel reason, some serial code, some parallel reason likewise. Fine. So I think up to here there is no doubt. So we will move further. So this is the one example we will going to see here, so that how this program is parallelized and what are the features that has been used. So your program is starting from here. Okay, we are having some variable sum. There are two arrays. So it is a summation of it is a multiplication of two vectors and the sum of that value. Fine. So two vectors are there, a and b. Then the size of n is 256. So there are 256 elements. Now this is the simple code over here where we are just initializing the value of a and value of b. Then sum is equals to 0. Now here this is the particular statement by which we can make this program or this part of code is parallel. So most of the time what we have to do, we have to see where the computation is going on. Okay, where the computation is going on, and we have to see the loops, because the loops they are iterating so many times. So now here you can see the loop will get iterated 256 times. Yes, 256 times the loop is getting iterated. So that is the one particular part where we can target to parallelize. So we will not going to target the initialization, we will not going to target the output printing, we will only target where the computation is going on in the code, and just before that we can add hash pragma omp for, because this is a for loop, and this is one of the clause called as a reduction clause, which we will see in the detail. The job of this clause is to perform the specific operation and to accommodate the result in a particular variable. So sum is the variable, and in that sum the operation is plus. So this operation plus is get applied and to get the final result which will be in the variable sum. And what is the code? Sum is equals to sum plus a of I into b of I. Okay, so here simply we are multiplying two vector and we are adding over here. So this particular task will be get executed in parallel. Now in this case we have not specified any number of threads. Okay, so what happened in this case? Whatever may be the number of threads available on your machine, that all threads will get allocated to this region by default. Okay, if you are not specifying. So if suppose your machine is having 4 cores, so it will create 4 threads. If your machine is having 8 core, so it will going to create 8 threads like this. And at last we are printing the result of sum. Fine. So see how simple it is to apply the OpenMP in this particular code. So moving further, how to compile and execute OpenMP program. Okay, so compilation and execution of OpenMP program we have to see here. So this compiler is available in the GNU GCC compiler with the version 4.2 and higher. So your version of compiler must be 4.2 and higher. So automatically OpenMP is available. The header file you have to add this. The compilation step is this GCC. If your C program is there, and if it is a CPP program, it is a G++. So GCC-F OpenMP, this flag you have to add, so that by adding this flag, it will interact with the program and identify where that OpenMP code is written in the program. And then your simple file, which is program file.c. Here we need not to make any change in the extension. It is .c file only. And how to execute? Just / whatever that executable. So it can be a.out or it can be any other file name without any extension. So these are the simple way by which we can compile, we can execute the program. Now moving further, what OpenMP provides? Okay, what are those features by which I can write down the OpenMP program? Fine. So it is a set of compiler directives, that is the first. So example of compiler directives are parallel, for. These are the examples of compiler directives. Simply we have to add, and compiler will understand, okay, parallel reason start, okay, parallel for loop is started. Okay. Next, it is having a runtime library routines. So there are certain library routines. By calling that library routines, I can get the result. So let's say an example, I have listed 2, but there are so many library routines. So these are the heavily used routine. So what is the first one? OMP underscore get underscore thread underscore num. So it will going to tell you that what is the ID of the thread. Okay. So every thread the first thread, which is last thread, it will to have the ID 0, then next thread will have ID 1, then 2, then 3, then 4, likewise. So by using this particular method, we will know what that suppose you want to perform, you want to assign a particular job to a thread number 0. Okay, so that time by using this particular method, you can get the ID, and if the ID is equals to 0, so then you can assign the task. Now the next runtime library is OMP get num threads. So by using OMP get num threads, what will happen? You can know how many threads you have created. Okay, how many threads you have created. So with that you will know, okay, for this reason you have created 8 threads. So that is for your you should know that these many threads created in the parallel reason. Now next we are having some environment variable. Okay, the environment variables are very known. They are with respect to different software. Here also we are having some environment variables with respect to OpenMP. So I have listed 2, but there are many. So OMP underscore num underscore threads. So by using this OMP underscore num underscore thread, what you can do, you can specify the number of threads. Okay, you can specify number of threads for your program. Whether it is a 4, whether it is a 8, whether it is a 16, whether it is 32, 12, 10, whatever it may be. So that can be easily done. So this particular thing you can set on command line only. On command you can just use this and you can specify what is the number of threads. Then OMP dynamic. This is also one of the environment variable. If you say OMP dynamic, that means you can able to use the nested parallelism. Okay. So nested parallelism is not available default. For nested parallelism, you have to create this OMP dynamic. So automatically the nested parallelism get enabled and your program will use that functionality. So these are the facilities or the functions in terms of compiler directives, runtime routine and environment variable provided in OpenMP. Now there are certain guidelines that we need to follow whenever you write a program. These guidelines you follow strictly so that you can get a good program written in OpenMP. So first guideline is create team of threads for parallelism. So create it, specify how to share work among the member of team. So we have to specify as a programmer that the work which will be get shared among the number of threads. Fine. Declare both shared and private variable. This is very important. If you will forget to specify this, everything will be shared. So when everything will be shared, there is a chance of inconsistent data. Then next, synchronize thread and enable them to perform certain operation exclusively. So synchronization has to be provided as and when it is needed, so that certain operation they need to be executed consistently, so that after execution of that you can see the consistent result, or the data must be in consistent state. So now what exactly we have to target? So sharing work among threads. So that is the one of the thing. What is that particular work which we have to give to the thread? So OpenMP work sharing directive are provided for programmer to state how the computation in the structured block of code is to be distributed among the thread. Okay, so there is a particular code, okay, which we want to execute in parallel, and moreover to execute that code we are having lots of data. So how that lots of data in that particular code need to be executed, that we have to investigate. So what we do, whenever you have a code, what you do the first thing, where are the loops? Just you target the loops and you see what are the loops they are performing the actual computation, not initialization, not printing the result, the actual computation done by the number of loops in your program. And then you investigate in that program whether there is any dependency or not. If dependencies are there, so you have to resolve the dependency if possible. Okay, and if there are no dependencies, so you can directly apply OpenMP on that, and you can speed up the program towards to get the result. Fine. So the next thing is OpenMP memory model. So just already I have told you, but still we have to see once again. So OpenMP is based on shared memory model. So whenever memories are shared among the threads on that particular platform or hardware, you can use OpenMP. By default, data is shared among all the threads. Okay, so that is the by default. That means exclusively we have to specify what comes under the category of shared data, what comes under the category of private data. Then next, data can be private to thread also if specified. So certain part of data we can make private to thread, so that only thread will know that data and they will update that data as and when it is required in the program. And that data they may also send to the other threads, but that can be done through programming only. They will not do like this, okay? Automatically things will not done. Through programming only that can be possible. Now moving further, the performance consideration. So now suppose you are having one C program, fine, and that C program you have converted into the OpenMP program. So now you have to measure the performance, that how much speed up you have achieved from the parallel program out of serial program. So that can be easily calculated by using this formula, that S is equals to T that is TL, that is a serial, and TPI, that is a parallel. Okay, so speed up is calculated the time required for serial execution divided by time required for parallel execution. So you can get a speed up. But moreover, we are having a law given by Amdahl's. So Amdahl law also specifies the speed up. The speed up is given by 1 by this particular formula, where 1 by divided by F fraction. What is this F par? This is the fraction of the code will get executed in parallel. Okay, fraction. Your entire code you are not going to parallelize. In the whatever the C code which you have, in that only part of the code you will parallelize. Okay, part of the code. So that part of the code can be 20%, can be 40%, can be 60%. Okay, so that is exactly F bar, and this P indicates number of processors. So this particular parallel fraction will get executed by number of processors plus 1 minus F par. What is this? This indicates the serial code. Okay, this indicates the serial code, that this is the particular code which is will get executed in parallel, and this is the code which is getting executed in this is will get executed in sequential, and this is executed in parallel by taking the help of p number of processors. Okay, so it is not like this that you will keep on increasing the number of processors, so you will going to get more speed up. No, it is not like this. It is totally depend upon what particular code you are executing and what is the behavior of that code. Okay, that only determines how much speed up we can get, and moreover in what way we are exploiting the hardware. Fine. So this is the law given by the Ambells, where it says that only fraction of code is get parallelized, and that can be parallelized by p number of processor, and the remaining serial code will be as it is there. Fine. So if we will take an ideal condition that this particular code is parallelized completely, okay, so the speed of will be the number of processors, because this term will going to become 0. Okay, 100% code is parallelized, so F par will going to become 1, so this is a 0, and this P will go up, so speed up will be the number of processors that are applicable, but that is not going to happen. Complete code we will never going to parallelize, only the part of code, okay, only the part of code we will going to parallelize. Fine. So now moving further, what are the OpenMP directive construct? Because by using item the OpenMP program. So we are having the OpenMP directive and constructs are parallel, task, work sharing construct, thread private, and synchronization construct. So in parallel, because this is more important, because we have to create a parallel region, so we require a parallel construct. So parallel, we are having a parallel to, parallel for, parallel section, parallel work sharing. So out of that, parallel do it is for Fortran, okay, and parallel work sharing it is for Fortran. So available for C and C++ is parallel for parallel sections. Okay, so by specifying this, I can say the loop is, for loop is get parallelized. By specifying this, the different independent codes can be parallelized. Now then, work sharing, we have to share the work. Okay, we have to share the work. So for C and C++, these are the work sharing construct, that is a for, because inside the for I can have lots of computation which will be done through number of iterations. Then there may be a number of sections, independent code that can be executed in parallel, or work can be shared among the single thread only, and this is available for only Fortran. So for, section and single. So in a single, only one thread will get executed, so it can be any thread. Sections, number of threads will execute the independent sections in parallel, and in for loop, number of threads will going to execute same task but for different data values. Then there is a thread private. So this is the construct which helps you to make the data available to the thread which is a private. Okay, so that data will be private to the thread only. Then we are having a synchronization. This is one of the important aspects in OpenMP or in any parallel programming language, whether it supports a good facility of synchronization or not. So synchronization can be done by using a master, by using a critical, by using a barrier, by using a task wait, by using atomic, by using a flush or ordered. So these are the different clauses. Okay, so by using these different clauses, we can synchronize the particular synchronize the threads when they are executing a particular code. Okay, so we will see this all in detail. So this is an overview what exactly the OpenMP altogether have. Now then, there are, so not all the clauses are valid to all directives. So we are having so many clauses, yes, but not all are valid to all the directives. So we are having directives, these are all the directives, and under these directives we can use a clauses. Okay, under this we can use a clauses. So all clauses are not valid for all directives. So what it says that most of the clauses except a comma separated list of items. So whenever you are specifying a clause, let's say an example, this default shared or none. So after that, if you want to use private, first private, so you can put a comma and then you can specify. If you want to use a reduction, so you can put a comma and you can use a reduction. So likewise, it is allowed. All list item appearing in the clauses must be visible. Whatever the items, list item means the variables. The array you are using, one dimensional array, two dimensional array, or another variables. All the variables are clearly visible whenever they are specifying with respect to clauses. So take an example, see here, shared. This is the list. So here I will specify all the variables. Those are shared. Those data value will be shared by all the threads. Here also. So if you miss here, so definitely your program will going to give the incorrect result. Okay, it will execute, but it will going to be incorrect result. So in that way, we are having some data, and then there is a data sharing attributes, and then there is a data which is a data copying attributes. So data sharing attributes are like this: default, share, none. Shared variable can be specified by this, private variable by this, first private by this, last private, and reduction. Here, whenever we are executing in OpenMP, what we have to do, we have to specify the schedule. In what way that entire work will be get scheduled by the number of threads. So we are for that, already we are having the 4 kind of schedules available in OpenMP: a static schedule, dynamic and guided and runtime. This schedule will help you to execute the task. Okay? So there has to be a proper strategy, yes? So without that strategy, execution of the work will be not proper. So that can be done by using this. So we will see in detail when we are going to see an example on static, dynamic, guided and runtime. So now this is the structure of your parallel construct. Okay? The structure of parallel construct. So what the purpose of this construct is? Parallel reason is a block of code that will be executed by multiple threads, and that is the fundamental OpenMP parallel construct. So we have to write down pragma OMP parallel and then all the clauses here you can specify. So you can use if clause, you can use a private, shared, default, first private, reduction, copy in number of threads, and from after that structure block will start. That is the code which we want to execute in parallel. Okay, the code which we want to execute in parallel. So this is the particular statement that we have to add before the code which we want to parallelize. Okay, the code which we want to parallelize. Before that, just this one line we have to insert with over the number of clauses which you want to use. So what that parallel construct altogether helps you. So when threads reaches parallel directive, it creates a team of threads and become the master of the team. Okay? The master is a member of that team and has thread number 0 within the team. So whenever parallel directive is reached, so that time the team of threads is get created. In that thread, we are going to have one master whose ID starts from 0 and the remaining threads ID will be 1, 2, 3, 4 up to n minus 1. Starting from the beginning of this parallel reason, the code is duplicated and all threads will execute that code. So whatever the code which need to get executed in parallel, internally that code is get duplicated with respect to number of threads. So if 4 threads are there, so there will be a 4 duplication of code, and that code will be given to the threads and they will execute that code where they will handle different data values. Next, there is an implied barrier at the end of parallel reason. So whatever the parallel reason which we have, already there is some implied barrier, okay, at the end. So that means all the threads has to come at that end, okay, and they have to visit that particular barrier and all the threads will disband. All the threads will destroy at that point. Only one thread will remain whose ID is equals to 0. If any thread terminates within a parallel reason, okay, it may possible due to some problem. If any thread terminates within a parallel reason, all threads in the team will terminate. That means it is as simple as that. If one of the threads is not participating in the computation, the whole computation will collapse. Okay, whole computation will collapse, and the work done until that point is undefined, because you have created a 10 threads. 8 threads they have done their work, but 2 threads they have not done their work. That means that part of computation is remaining, which is undefined. So due to that, that entire operation is a collapse. So that should not happen. Okay, when the number of threads are created for the reason to perform the task, so these all threads need to execute those tasks. Okay, if they are not doing, so that there is a no meaning of that particular parallel reason, and the remaining task will be undefined. So now this is the first parallel program, okay, where we are just want to print hello world. We want to print by the number of threads which we have on a machine, and moreover what we will do, we will print how many threads are there, and we are going to print the ID of each and every thread. They will going to print hello world from hello world. This is the message. So just see over here, it is very simple program, omp.h. These are the two variables that we require. N threads. N threads will going to handle the number of threads, and TID will going to handle the ID of the thread. Now here the parallel reason starts. So pragma OMP parallel private. So here I am specifying TID is the private. So whatever you specify TI private, that particular variables. Yes, N threads and TID. TID is private, that means every thread will have its own copy, but N thread is not private. That means if it is not specified here, that means N thread is shared. That particular variable is shared by all the threads. Fine. Now this is the parallel reason starts, the curly bracket, and here we have to specify the operations which will get executed in parallel. Okay. So see what we do here, we are calculating the TID. So TIDs get calculated by OMP get thread num. So this will going to give with the thread ID, and that thread ID will be available with each and every thread, because private TID is a private variable. Fine. Then what we are doing, we are printing the message hello world from threads. That means hello world from thread, and here thread ID is getting printed. So this message will get printed by multiple times by number of threads. So if there are 4 threads, this message will get printed 4 times, where it will indicate who that, what are those threads they have printed. So thread number 0, thread number 1, thread number 2, thread number 3, likewise. Then here what we have, yes. So here what we have done, here we are making one statement that only TID is equals to 0 will go to execute this. Okay, so that already told I have previously, you can assign the task to the respective threads also. So by TID, so only TID is equals to 0, that is a master thread, will perform this task. So this task will get executed only once, but this is the task is executed many times by the many threads. So what we are doing over here, n threads is equals to, we are calling a method where it will going to give you how many threads are created in this parallel reason. So that will be available here. Then what we are doing, we are printing a message. So this message will get printed by the master thread. Okay, so that ID we are printing by this method. And then here we are printing number of threads. So that will be get printed by this variable. So these two statement, this and this will be get printed once, and this is getting printed many times. And then here we are closing the parallel reason, and then your program is closed. So you will see the output for this. So let's say on my machine, if I have 4 threads, so I get the output like this. Hello world from thread 1, hello world from, here you can, this is not getting खरं मी केलं करेक्ट.
हां, बोला की. कोणत्या सॉईलमध्ये? बरं, बोला की. आले का छोटे? किती एच.पीचं आहे? 26 एच.पीचं आहे का? चालेल. आता आम्ही मध्ये कुबोटा घेतला तुमचं चर्चा झाल्यानंतर, तुमचं काही येईना म्हणून. बघा आता हे. हं. आम्ही लॉकडाऊनमध्ये घेतला कुबोटा 27 एच.पीचा घेतला. तुमची किती प्राईस आहे? 525. बरं बरं, म्हणजे 4.5 पर्यंत भेटेल. बरं, येईल शोरूमला, एक दोन दिवसांनी येईल शोरूम.
So sorry for interruption, my connection was loose. So now we are going to see the hands-on on OpenMP. So it is not possible to cover all the concepts of OpenMP in that stipulated time, but it is always better to have an exposure in terms of how we can program. Fine. So I think I am audible. Can anybody respond me? Am I audible to everyone?
Yes, sir. Audible.
Yeah. Thanks. So I'll share my screen for the lab. Fine, thanks. So we'll see the programs. So before to start working on OpenMP, just we have to see whether OpenMP is available on our machine or not. Okay, so for that what you can do, you can simply type this command gcc -- version. Okay, so because first of all we require a GCC. So if GCC is there, so that GCC we have to check by using gcc -- version. If it is there and you will get this message, that means the entire functionality of OpenMP is available. Fine. So with this we can move further. So I am doing some programs with me. So we'll start with the programs one by one. Okay, so I think my screen is visible to everyone. So the first program is where we want to demonstrate how hello world can be printed by number of threads. Fine. So hello world we want to print. There we want to take the help of OMP get thread num, and then we want to use a OMP get number of threads. So thread num will going to give the ID of the thread, and OMP get num threads will give you the total number of threads. Fine. So your program is very simple, not much difficult here. OMP.h is added. This is the some printf statements, which is not that much important. Now here, what we are doing, OMP set num threads we are doing, which is 4. Okay, 4 threads I am assigning for the parallel reason. So that I am doing before the parallel reason. Fine. And this is my parallel code, pragma OMP parallel, where I am saying that private is thread ID. So thread ID is private. That means this variable will be available with all the threads, and they can do the changes on that variable. Now here I am just calling the method which will going to give me the ID of each and every thread that is stored over here, and here just I am printing the message my thread ID and then ID. Fine. And after the parallel reason here we are making one printf statement. Okay, this printf statement is getting printed by master thread. This statement is getting printed by all the threads. Fine. So now I will going to compile this and I will show you how that can be run. So gcc -f OpenMP and the program. So program is example1. Okay, this is my program example1 _1 -o and exp1. This is my executable exp1. So now my program is compiled successfully. Now I have to run it. So dot exp1. That's all. So what I got? I got the output like this. So master thread prints this before forking the T. So there are two statements which will be get executed by master thread only, and there are this statement which will be get executed by all the threads. So now I have indicated 4 threads. I can increase that also. Let's say I do this 8. Control S. So now I'll compile it. Now I'll run it. So now see, 8 threads are created. You can create as many threads you can, but it is always advisable that just you see how many cores are there, and according to that many cores you create the threads. Otherwise, thread will be in the waiting state, because at a time the number of cores are there that will be active. Okay. So if you are having a 4 threads, 4 cores, so create only 4 threads. If you create 8 threads, so at a time 4 threads are active, then 4 thread will be in wait. When this thread will going to finish, they will going to get a chance. Fine. So this is the one simple program which we have seen here. Now moving towards the next program, which is program number 2. This. Now it is similar to that only, just little change we have done in this case. So what we want to do here, we want to once again print hello world only. We are using OMP get num threads and OMP get num threads and thread num. Okay. So there are two variables. This variable will handle thread ID. This variable handle number of threads. Now in this case, what we are doing, we are not specifying how many threads that we want to use for the parallel reason. This is the parallel reason. Yes. Here there is no specified. Nothing is specified. So pragma OMP parallel. This is the private clause. This variable is the private, and all other variables are what we say shared variable. So here I am calling the method which will going to tell you the thread ID. Here I am with respect to thread ID 0, this work is done. Okay. So hello world is being printed by multiple threads, and this last statement is get printed by one thread, and this is the statement getting printed by one thread only. Fine. So now we will compile this and we'll see what result we get. So this is the example 2 1.2. And it is example 2. So now it is compiled successfully, and now it is second. So see, so on my machine I am having 8 cores. It is a default. Okay, the program, if you see here, we have not indicated any number of threads. So on my machine I am having 8 threads. Okay, 8 core, so that's why automatically it has identified, and this statement is getting printed by 8 threads, and this statement is get printed by one thread, and this is get printed by another one thread. So this is my output. So hello world is being printed by thread 0, then 1, 2, 3, and master thread printing total number of threads for these executions are 8. Okay, so this is the way the number of threads can be controlled, or if you don't want to specify, automatically it will take the number of threads available on your machine. Now moving further, third example. So in the third example, what we want to see, so program for parallelizing the loop nest containing recurrence relation. Okay, so this is one of the example where we are having some recurrence relation. I think you are aware about the recurrence relation. In recurrence relation, what we have, the current instance which you want to compute, it is depending on the previous instance. Okay, the previous, it is similar like a recursion kind of thing. So the current instance, if you are calculating t of n instance you are calculating, so you have to calculate t of n minus 1 instance, then you will going to get the result. So here we are using one matrix. So we have to enter the size of the matrix, and we have to enter the number of threads. And what we are doing over here, each thread does the row-wise recurrence calculation. Okay, this is the crux over here, what exactly this code will do. So it is a demonstration code where loop nest containing recurrence relation is there that we need to perform in parallel. So the input we have to give matrix size and the number of threads. Okay, so you will see in that. So the main code, whatever is there, that we are going to target. So here we are having input matrix. This is a check matrix. So this check matrix will be having some values which we have to check with respect to the output. Then certain variables. Okay, now here this is the command line program. So on command line I have to pass some variable. So variable means the values. The values are number of threads and the matrix size. Next. Now here I have made some control that this particular code will be get executed. This executed, the number of threads should be 1, 2, 4 and 16. If it is 3, 5, 7 or something like this or more than 16, so it will not execute. Okay, just for a fun, nothing else. Now what we have to do here next is we are allocating the memory dynamically. Okay, so try to use a dynamic memory allocation for your program. Don't go for static memory allocation, because the static and memory allocation, they are having a certain limits. Up to certain limit you can allocate the memory, but by dynamic memory allocation you can utilize this heap space and you can utilize the maximum memory available on the system. So input is getting input matrix memory allocated, check matrix memory allocated. Here we have initialized the value, that is input matrix value is initialized at this point. So any particular value I plus j I have done, and then similarly there is a check matrix. Okay, so for check matrix I have assigned the value of input matrix only. Fine. Now then what we are doing over here I am setting the number of threads. So whatever the command line value we will set, that value will come at this point, which will be the number of threads. Now here what we are doing, so first of all we need to know what is the recurrence kind of statement. So recurrence kind of statement is something like this. Here, fine. Serial input matrix ij is equals to input matrix ij plus input matrix I j minus 1. So now here it is a two-dimensional matrix. Fine. And now here whenever we are calculating input matrix ij, it requires j minus 1 value here. It requires j minus value here. So to do that, so here this jth loop you cannot parallelize because it depends on this. Whenever you will parallelize this, j minus 1 instance is required to have the value for j. Fine. So what we are doing, if you see this particular code, I have parallelized only the ith loop, because in ith loop it is using same indices. Okay, no I plus 1, no I minus 1. So there this loop is getting executed in parallel, and whatever the jth loop is there, that is getting executed in serial only. So the task from here to here, it will done in parallel. Okay, so from here to here, this complete for loop from here to here will done in parallel. So the ith value is parallelized, and in that way the loop is getting executed. So this way we can see. So whenever such kind of statements are there, just you see what you can parallelize. Fine. And then this is the parallel code of the same thing. Now here this is a serial code. Okay. So for serial code, just the way we write, we have to write the program. Now here this is the code where what we are doing, we are checking whether the result of parallel code and the result of serial code is same or not. Okay, so just we are checking. If it is equal, the loop will get continued, else this message will come. So we don't want to get this message. Okay, if our program is correct, we don't expect that this message will come on the screen. Fine. And then at last, just we are printing the number of threads, the matrix size, and the serial computation are same. Why we are printing this? Because here we have already checked it is correct. So when it is coming from this loop and it is coming here, that means everything is okay. Fine. And at last you have to free the memory. So memory will be freed at last at this particular point, because dynamically you are allocating the memory, so it is the responsibility of the programmer to deallocate the memory. So now we will see how that program can be run. So it is the experiment number 3. Okay, so program executed successfully. Now we have to see, we have to run the program. So now it is a command line program, so only executing this statement it will not work. You have to pass the parameter. What are the parameter? The number of threads and the matrix size. So let's say pass the parameter. So let's say number of threads are 8 and matrix size is 1024. So what we got? The demonstrated. Now we got the result. Serial and parallel calculation are same. That means the code which we have prepared in parallel, it is synced with the computation result which we got from the serial. So total number of threads are this, matrix size is 1024, and the serial and parallel calculations are same, because that we have tested in the program itself. You can increase the matrix size. So still the output is same. Still the output is same. That means the parallelization is correct. Now we'll see another program. So where we will going to see how to find the time also. Now here this is another program where we want to find the sum of elements of one-dimensional real array. Okay, sum of elements of one-dimensional array we want to find out in parallel. Okay, so in this case, when you will do this, you are going to find some critical section. Okay, what is that section we will going to see, and how that can be parallelized, that we will see. here you have to pass the array size and you have to pass the number of threads. These two things you have to pass. So directly we will go to that particular part where the actual code is written. All other code is just check kind of code. Okay, yeah, here. So here we are assigning the values for the array ai and array and check. So in array we will going to get the parallel sum, and in check we will going to get the the sequential sum. So array and check, they must give same result. Okay. Now here we are assigning the number of threads. So this variable will hold the number of threads. Now this is the reason where we are parallelizing. So pragma omp parallel for. Okay. And what is the statement that we have to do? Sum is equals to sum plus array. That's all. That is the only statement that we require. Sum is equals to sum plus array. But if you see here, this sum and this sum, so sum is written in the left hand side and sum is available in the right hand side. That means in the left hand side you are writing with respect to sum, and in the right hand side you are reading with respect to sum. So there is a chances of dependency. Okay. So here you are reading and here you are writing, so that if you without using pragma omp critical, you will not going to get the correct result here, because sum is you are not specified what is the sum. So sum is, in this case it is a shared. Sum is a shared. So what will happen when you will do this particular code here? One thread will enter at this region. Only one thread will enter and it will perform the task. Then next thread will enter, it will perform the task. So this is the way critical reason works at this point, because sum is a shared variable. Okay. Then here we are calculating the sum, which is a serial sum. And then here we are checking whether the serial sum and the sum, which is a parallel sum, it is equal. If it is equal, that means our results are correct. And then at last we are printing some statistic, that is the parallel sum and the serial sum. So I'll run this program. So it is executed, compiled successfully. Now we have to run the program. So for running the program, what it is expected, we have to specify the number of threads, let's say 8, and the size of the array, let's say 2048. We got a result, number of threads are 8, array size is 2048, the serial and parallel sum are equal, and their values are also equal. So this is produced by the OpenMP and this is produced by the serial. So in this case, both the results are correct. Fine. Now moving further, I have to directly go to some another problem where we can see the the timing. Okay, so let's see whether here we are having a timing or not. So here also we don't have a timing. 1.6. Here also timing is not there. 1.7. 1.8 we will see. One point 9. Yes, this is the program we will see in detail. So in this program what we are doing, our 1.10 we can directly take, because that will be more suitable at this point. What? Yeah, 1.10. Okay. So what we are doing in this program, write a program to demonstrate the performance improvement by doing the loop inverting. Okay, there is a concept called as a loop inverting. We know that in the memory, when you are having a two-dimensional array, it is stored in a row measure order. Okay, first row is stored, then next row, then next row, then next row. Fine. And suppose you are inverting here, so definitely it will not help you where suppose you are reading in a row measure order, so it will be more efficient. If you are reading in column measure order, so it is not much efficient, because most of the time the data transfer is required. Okay, because in that row only one value you are requiring, not all the values. So more and more data transfers are required at that particular point. So now in this program, what we are doing, we want to find out the performance. Okay, performance. So what exactly we are doing, that I am going to tell you here. So first of all, here we are initializing the matrix. Fine. Yes. Now this is the particular code where we want to apply the loop inversion. Fine. So see what happens. First of all, we want to discuss on that. So this section parallelize the sequential for loop into parallel for loop. Because of data dependency between two rows, there will be a data dependency between two rows. The two rows cannot be updated simultaneously. You cannot update two rows simultaneously. That is, the loop index j can be parallelized, but index I cannot be. So see, this is your code, and this is the statement. Matrix I comma j is equals to 2 times matrix I minus 1 j. So here the jth loop you cannot parallelize. Okay, this is fact. This is the data dependency which you already learned in the previous sessions. So here there is a dependency, but with respect to j there is a no dependency. Yeah. So what we can do, we can apply the parallelization for j loop, not the parallelization for ith loop. Fine. But if the parallel for loop inserted before the inner loop, okay, if inserted before the inner loop, the resulting parallel program executed correctly, but it may not exhibit good performance. It is saying that it will not execute. Why? The reason is that here, what this is the parallel for loop. Okay, so whenever I am applying a parallel for loop, what will happen? It will going to create the number of threads. Yes. So, but this parallel loop, okay, whatever you have, this is inside this loop. That means the outer loop will get executed in sequence, but inner loop will get executed in parallel. Okay, so what happens when I is equals to 1, the control will come here, it will create the team of threads, fine, and then it will disband those all threads. When I is equals to 2, so once again the number of threads are getting created. So here 4 can join, again and again will going to happen. So due to that, the result is correct, but you will not be able to get good performance. And that 4 can join will happen with the matrix size minus 1 times. This many times 4 can join, we have to perform. So due to that, it will going to degrade the performance when I am applying the for loop over here. That is the parallel OMP for loop at this particular point. So this is one code. Okay. Now we'll see another part. Here we are measuring the time as well. Okay, this get time of day function is there in the Linux, which will help you to get the time. And here we are recording the time, and here we are printing the time. Now the same thing. Okay, and here yeah, fine. And then here, so this will not going to help at all at this particular point. So what we can do, you can invert the loop. Okay, you can invert the loop that you can see over here. So what I have taken, jth loop is outside and ith loop is inside. So with respect to jth loop, everything is get parallelized. So we will see the performance of this code and we will see the performance of this code at this point. So the timing I have measured at this point. So timing 1. Code and timing 2 for this loop where loop inverting we have done. So this section parallel the sequence of loop into parallel because the data dependency between the two rows and two rows cannot be updated simultaneously. The means of the loop j can be parallelized, but I cannot. If the loop is inverted, then apply parallel for before the outer loop. Only single fork join step is required. So in this case, only once fork and join will be takes place, and there will be no much overheads. So we'll see this and we'll see what is the output we get. So this was the 10th program. So there is a cost function, so we have to add the cost function over here. Dash lm. Okay, so now it is executed. Now we'll run the program 10. what is required, number of threads and matrix size. So number of threads are 8, matrix size is 2048. So here you can see, so code, so now the first one is, we have just parallelized, so we got 28205, and when we are inverting, so we got 2387. That means in the second part of code we are getting the less amount of time, and the first part of code we are getting the more amount of time. So this is the way you have to think for better, means that is exactly as some kind of an optimization in terms of just changing the pragma from one for loop to another for loop. Fine. So at this point I stop because there are so many, we are just lack of time. So if any doubts are there, so I will take all your doubts. So I open for questions if any at this point. So any doubts are there, you can ask. So any doubts you can ask me. So regarding contact, just you visit IIT Nagpur, so you will get all my contact details. So all contact details of each and every faculty of IIT Nagpur is available on the website. Okay, so thanks to everyone for your patience.
Hello, sir.
Yes.
Sir, one question is there. Can you use the Python platform for OpenMP?
Python platform for OpenMP, yes, you can use.
Thank you. Okay, thank you, sir. Thank you, everyone. We will start the next session at 12.
Okay, fine, fine. Thanks.
Okay, thank you, sir.
Yeah.